So we are moving on to the next topic. We've talked about group 1. We've talked about group 2. It's time to focus on group 4. We're skipping group 3. We'll talk about those later. But we're moving on to group 4. Group 4 is aromatic compounds. Benzene is an aromatic compound, as are these things. We'll talk about those things in a bit. Benzene, it's aromatic. We'll talk about what that means to be aromatic in a moment. But benzene itself is C6H6. It's not very reactive. It's an inert compound. It's used as a solvent in some things, or let me say, it used to be used as a solvent in a lot of reactions before they found out it's not so good for your health to be exposed to a lot of benzene. But benzene typically does substitution rather than addition, and only when forced. Why does that matter? Why is that a big point to make? Benzene has 3 pi bonds, and things that have pi bonds, we've said traditionally do addition reactions, like a normal alkene does addition reactions. But benzene does not behave as a normal alkene because it's aromatic. It does not behave as a normal alkene, so it typically does substitution rather than addition, and only when forced. Yes, there are 3 pi bonds and 3 single bonds in benzene, but because of resonance, all bond lengths and strengths are the same. Yep. So we've said at least 3 times in the last minute and a half that benzene is aromatic. What does it mean to be aromatic? Cyclohexene, here's cyclohexene, it's got 1 pi bond. To turn cyclohexene into cyclohexane, that's this bottom energy shelf down here, to turn it cyclohexene into cyclohexane, the hydrogenation, the energy of hydrogenation, is negative 28.6 kilocalories per mole. So when benzene has 3 pi bonds, you would imagine that the energy required, the energy released, would be 3 times as much. So 3 times as much is negative 85.8. So if you considered this cyclohexatriene, this benzene-looking thing, but without calling it benzene just yet, cyclohexatriene is predicted to have this stability. But as it turns out, this cyclohexatriene, which we now know as benzene, is more stable than that. It releases 49.8 kilocalories per mole when you hydrogenate it. There's some sort of reason that benzene is at a lower energy shelf than what's predicted. Aromatic compounds are more stable than the normal prediction would have them be. This is normal prediction up here. This is benzene. Because of delocalized electrons, you lower the energy. So that's saying there's 36 kilocalories per mole. It is 36 kilocalories per mole more stable than as predicted. All aromatic compounds are more stable than as predicted. Whew, that was real bumpy. All right, what does that mean? When you have a normal benzene with a normal alkene, we've learned that H2 and nickel, that's hydrogenation, and the hydrogenation of that thing should lead to this compound, where you leave the pi bonds in benzene alone because they're super stable as an aromatic compound, so it's not easy to get them to react. But if you have high heat and high pressure, you can get those pi bonds in benzene to react, and you can reduce benzene into cyclohexane. And the actual energy cost we just mentioned is that, to get benzene to become cyclohexane. Yeah. Okay. So because benzene has all these pi electrons, it's more stable than the molecule, the normal Lewis structure would predict. What the heck? Benzene has all sp2 carbons, and sp2 carbons have an unhybridized p orbital. And in benzene, those unhybridized p orbitals are being used to make pi bonds. Well, sp2 is called hybrid orbital theory, but we now know of something called molecular orbital theory, which we think is a better description of how molecules bond. So rather than thinking of these 6 atomic p orbitals, we recombine orbitals along the whole molecule of benzene. The ones below the midpoint we call bonding orbitals. The ones above the midpoint we call anti-bonding orbitals. So when you take benzene's 6 pi electrons and distribute them in these molecular orbitals, you end up with 6 electrons in bonding molecular orbitals. Anytime you can completely fill bonding molecular orbitals, that's great news, and that molecularly is why benzene and other aromatic compounds are more stable than their molecule predicts. It's quite a bit more complicated than that, and you might say, well, I didn't understand the thing you just said anyway. It gets into some P-Chem kind of stuff to talk in any more depth than this, but we can chat individually about it if you would like. Okay, on to aromaticity stuff. Benzene is aromatic, but benzene is not the only aromatic compound that exists. There are lots of aromatic compounds on the face of the planet. In order to be aromatic, a compound must have an uninterrupted cyclic cloud of pi electrons above and below the plane of the molecule. What? It has to be a planar cyclic molecule, and every single atom in that molecule has to be sp or sp2 hybridized, because only when you're sp or sp2 hybridized do you have a p orbital available. So in order to be aromatic, you have to have these p orbitals so that you can have an uninterrupted pi cloud. So this little purple ring in the middle is trying to show you the distribution of the pi cloud. Picture A shows you individual p orbitals around the cyclohexane thing, benzene, and then B shows you the uninterrupted pi cloud. In order to be aromatic, you have to have an uninterrupted pi cloud like that. So it's got to be a donut above and below the plane of the molecule to be aromatic. Yeah. Additionally, the pi cloud must contain an odd number of pairs of pi electrons. There's another guy that figured that out, and he said, let's come up with a mathematical formula to represent this. That's called the Huckel rule, and that's 4n plus 2. We'll see this in action in a moment. Your goal is to recognize whether these things are aromatic or not. I bet you already know about one of them, but bear with me. So first question, is it cyclic? Yes. Is it cyclic? Yes. Is it cyclic? Yes. Is it flat? Yes. Is it flat? Yes. Is it flat? No. This one is showing you that it's not flat. It's actually bathtub shaped. Yeah, we got some crazy names. I know. This one is not flat, so therefore it cannot be aromatic. Okay. So got to be flat, got to be cyclic. Everybody's got to have a p orbital. Would you say all carbons in that thing are sp or sp2 hybridized? Yep. Would you say all carbons in that thing are sp or sp2 hybridized? Yep. So then the next one is you have to have an odd number of pairs of pi electrons. 1 pair, 2 pair, 2 pair, 2 is even, no way. 1 pair, 2 pair, 3 pair, 3 is odd, yes. This is aromatic. Not aromatic, aromatic. Yeah, it's benzene, I know. If cyclooctatetraene had been flat, it still would not fit the criteria for aromaticity because it's got 4 pairs of pi electrons. So, no. If we tried to do the Huckel rule for each of these, just to show you what the Huckel rule looks like, 4n plus 2 should be set equal to the number of pi electrons, not number of pair, number of pi electrons total. So in cyclobutadiene, that's 4 electrons. Therefore, n equals 1/2. And before we talk about it, I'm just going to keep on rolling. 4n plus 2 equals number of pi electrons in benzene, that's 6. N equals 1. And the last one, it's not flat, I know. But 4n plus 2 equals 8. That means n equals 3/2. We don't usually do a lot of math in here, but yeah, that's as hard as our math will get. Because this is not an integer, and this is not an integer, it's further support to say the first one and the last one are not aromatic. The middle one is an integer, therefore benzene is aromatic. Yep. There's a lot of evidence to put together to say benzene is aromatic. Okay. Things can get a lot more complicated than benzene. Is they is or is they ain't aromatic? I encourage you to pause and figure out is they is or is they ain't. This is me pausing, so you can pause. I just unpaused, but I realized I should have said, assuming these things are flat, without me telling you whether they are or are not. You don't know whether they are flat or are not. So, yeah, apologies. Assuming these are flat, which ones are aromatic? First thing, are they cyclic? Yeah. Second thing, are they flat? Well, we're assuming so. Third thing, does everybody have a p orbital? Do we have all sp or sp2 carbons in this? Yep, in that first one we do. All sp, sp2 in this second one, middle one, big one. Yep. All sp, sp2 in this cyclopentadiene. Ugh. No, not all sp or sp2 over there. That will show up eventually, I think. sp or sp2 in cyclobutadiene? Yes. sp or sp2 in this bottom, there we go, in this bottom thingy, bottom right benzene thingy? Yes. So this carbon is not part of the cyclic cloud. So you can still call this compound aromatic, but really it's that there is an aromatic functional group within this molecule. You're not worried about that sp3 carbon that's not part of your cyclic ring. This is your sp3 problem up there, and this is actually your sp3 problem down here, so that one's not qualified to even count pi electrons for. Alrighty, so then we go back and we count pi electrons. 1, 2, 3, 4, 5, 6 pair, not aromatic. 1, 2, 3, 4, 5, 6, 7, 8, 9 pair, yep, aromatic. I know we've already seen cyclobutadiene, not aromatic. And I know we've already seen benzene, yep, aromatic. Triple bonds, only 2 electrons count. It's got to do with the orientation of the p orbitals. Remember, in a triple bond, oh, I'm a bad artist. In a triple bond, you're going to have 2 p orbitals aligned in one direction to make a pi bond, and 2 p orbitals aligned 90 degrees from those. Oh, isn't that beautiful? Look up a picture on the internet. These 2 p orbitals on that center right there are 90 degrees from each other. So only one of them has a chance of sharing with the cyclic cloud to make the donut on the top or the bottom. So in a triple bond, you only count 2 of the electrons. So everybody's sp or sp2? Yes. Everybody's sp or sp2? Yes. It's cyclic in both? Yes. And what else are we missing? Sp, sp2 is cyclic. It's flat, assuming these are flat. Yeah. 1, 2, 3, 4, 5, 6, 7. 7, yep, aromatic. 1, 2, 3, 4, 5, 6. 6, nope, non-aromatic. It was already written there, I know. Okay. Some annulenes are aromatic. Annulenes are things that have alternating double single bonds. Yeah. We've seen cyclooctatetraene already. Assuming it's flat, it's not. But assuming it's flat, it has 4, no way. Assuming this other one is flat, it has 7, yes way. So this one on the right, this on the left, is aromatic. This one on the right is not aromatic. What does that mean? Not unusually stable. Yes, unusually stable. What it also means is aromatic things usually do substitution rather than addition, and only when forced. Non-aromatic things do simple addition reactions. Just like a normal alkene would do an addition reaction, it does simple addition reactions. In a proton NMR, you actually see the protons in different places when it's an aromatic ring versus when it's a normal alkene. It's really weird how different that becomes, but all of these exterior hydrogens appear in the aromatic region on a proton NMR. And all of those interior hydrogens, highlighted in kind of pink color, those appear somewhere else. Aromaticity affects a lot of things. It's very strange. Very strange. Okay. Polycyclic aromatic hydrocarbons. Oh, look, in the name it says aromatic. Are these things aromatic? Yes, they are. Because in each of them, they're flat. There's a cyclic cloud of electrons in all of them. They all have sp2 carbons only. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. They all have an odd number of pairs of pi electrons. Those are all aromatic. You can maybe kind of look at them and tell that it's just benzenes hooked together with a little bit of different orientation of the pi bonds to make it all legit. Yeah. Okay. This says ions may be aromatic as well. So we've seen cyclopentadiene. It is not aromatic because we had an sp2, we had an sp3 carbon right there. But if that sp3 carbon reacts with a hydrogen like so, we get this thing. This thing is aromatic. Wait, you say, what? I don't understand. I've only got 2 pairs of pi electrons. Yeah. This is where the Huckel rule really comes in as important. The Huckel rule says 4n plus 2, set it equal to the number of pi electrons. We actually have 6 pi electrons here. Why are there 6 pi electrons? Because those electrons can be delocalized through resonance. These electrons count toward your pi system. So we've got 6 pi electrons, and just like benzene, that means n equals 1. When n is an integer, it's aromatic. So you went from a non-aromatic compound to an aromatic compound. What that means is, or what that, in this example, that has an impact on the pKa of this system, the pKa of cyclopentadiene. Normal cyclopentane, if you had some sort of base, and I'm not even going to draw H minus because H minus can't deprotonate it, that would make this conjugate base. This says has a pKa, most hydrocarbons have pKa about 45. This guy specifically has a pKa probably around 60. So that aromaticity makes a big deal as far as the stability of the product that's created. The more stable the conjugate base, the stronger the acid. Do you remember that argument from week 1, organic 1? The more stable the conjugate base, the stronger the acid. So this acid is actually the same acidity as water because you make such a stable conjugate base. Such a stable conjugate base because of aromaticity. Yeah? Yeah. Okay, that's not the only ions. Here are some ions down below. Is this guy aromatic? No way, because he's got an sp3 carbon right there. Cyclopropenyl cation and cyclopropenyl anion. Are they? Aren't they? Both of them are flat. Both of them are cyclic. Both of them have sp2 carbons only. So 4n plus 2 equals 2. N equals 0. It always amuses me to get you guys to do math. 4n plus 2 equals 4. N equals 1/2. So this one is aromatic, while the other one right beside it is not. Yep. In this cycloheptatrienyl bromide, there's an sp3 carbon, not aromatic. But here, the cation is aromatic. Because I've got 2, 4, 6 pi electrons. 4n plus 2 equals 6. Just like benzene, n equals 1. Yep, it's aromatic. Uh-huh. All right. So to be aromatic means the molecule, experimentally, the molecule is more stable than theoretical calculations predict it to be. Yeah. To be aromatic means the actual observed molecule is more stable than theoretical calculations predict it to be. To be anti-aromatic means that you are less stable than theoretical calculations. The actual observed molecule is less stable than theoretical calculations predict it to be. In order to be anti-aromatic, you must fit the same first couple of criteria, depends on how you look at it, the same criteria as being aromatic, as in it has to be cyclic, it has to be flat, and everybody has to have an available p orbital. The other thing is it has an even number of pi electrons, pi bonds. Or it fits the 4n rule, where n is an integer. So 4n is equal to the number of pi electrons where n is an integer. We're going to rewind and go back to the beginning of our examples and see some of the things that we labeled anti-aromatic. Should we have labeled them actually anti-aromatic? So here we are again. Should we have labeled these things anti-aromatic? This one, yes, it's anti-aromatic. Again, does that mean that this molecule is crazy unstable? Aromatic. Does that mean this molecule is crazy unstable? No. It means it's less stable than the molecule, than the Lewis structure would predict. That's all it means. This one is still not anti-aromatic. This cyclooctatetraene, octatetraene, is still it's still non-aromatic, not anti-aromatic either because it's not flat. But cyclobutadiene is flat, and it has 2 pair. That's an even number. And if we did our little 4n equals 4, n equals 1, yeah, anti-aromatic. We labeled this first one not aromatic. Should we have labeled it anti-aromatic? Yes. Because 4n equals 2, 4, 6, 8, 10, 12, n equals 3, that's an integer, it's anti-aromatic. The blue crossed out one is still blue crossed out because you gotta have sp2 and sp carbons. That's sp3. We've already talked about this guy is anti, and we've already said that that sp3 carbon in this bottom example doesn't qualify. Okay. We said the one on the left is aromatic. We said the one on the right is not aromatic. But really, we should have called it anti-aromatic. You don't see a ton of stuff about anti-aromatic beyond this first introduction to it. 2, 4, 6, 8, 10, 12. But all it really means is you're less stable than the molecule the Lewis structure predicts. Yeah. Okay. Nope. We got a lot of pop-ups to do here. We already know that cyclooctatetraene is not planar, so we won't really refine our definition there. But if it were planar, it would be anti-aromatic. These were all aromatic. This one, definitely not aromatic. sp3 carbon. Now this one down here, we actually should label as anti-aromatic because it's got 4 pi electrons. N equals 1. Yeah? It's real crowded on this slide, I know. But this one we labeled as non-aromatic because it's an sp3 carbon. It's not anti-aromatic either. This one we labeled as aromatic. Yeah. Okay, we're back to where we were. So you saw those molecular orbitals of benzene previously. One quick way to determine where the molecular orbitals should actually show up is when you have a cyclic thing, draw it standing on a point, like that point right there. Draw it standing on a point, meaning don't draw it sideways like this. Draw it standing on a point, and at every vertex, that's where you put your energy shelves. So that's how we get those 6 energy shelves over there. Okay. If we have benzene, how many pi electrons in benzene? 6. 2, 4, 6, like that. Fill up your 6 pi electrons and you get all electrons in bonding orbitals, and it's full bonding orbitals. That's great news. That's an aromatic compound. What if you have a 5-membered ring? Again, stand it on a point, and at every point, at every vertex, that's where you put your energies. That's where you put your molecular orbital energies. Okay? So this molecule has 6 electrons, so that actually must be representative of something like that. 2 pi bonds and 1 lone pair. That's an aromatic compound. All electrons in bonding, and bonding is full. Something like this has 4 pi electrons. Bonding is where all the electrons are, but all the bonding is not full. That's anti-aromatic. This bottom one has 4 pi electrons. That's 4 pi electrons. That's also anti-aromatic. So the vertical place where you put these energy orbitals is, there's a shortcut to tell you where to put those orbitals based on the vertex of the cyclo thing you're looking at. One little thing I want to point out in this last one, because those orbitals are right at the midpoint, those are called non-bonding. Anything above the midpoint, anti-bonding. Anything below the midpoint, bonding. And in order to be aromatic, you have to have all electrons in bonding, and bonding has to be full. Any other thing, you're either non-aromatic or anti-aromatic. Yeah? Okay. Some heterocycles can be aromatic as well. What the heck are heterocycles? Heterocycles means a ring that has something other than carbon in it. So pyridine, we've seen him a lot recently. He's an aromatic heterocycle. Let's talk about why. In all of these aromatic heterocycles, you have to consider whether the lone pair on the heteroatom is vinyl or allylic. All of these nitrogens have a lone pair. And some of them, yes, this is an option, I know, and some of them are vinyl and some of them are allylic. And if they're vinyl, they don't count toward your aromaticity, toward your pi cloud. And if they're allylic, they do count toward your aromaticity, toward your pi cloud, but only one pair. Why? Well, if we look at pyrrole quickly, pyrrole has a lone pair on nitrogen. That lone pair is in a p orbital. How do I know that lone pair is in a p orbital? Because the hydrogen is in the hybrid orbital, and the 2 bonds to carbon are in the hybrid orbitals. So it leaves that lone pair in a p orbital. That lone pair in a p orbital is allylic to your pi bonds, meaning right next door to. Not directly connected, but right next door to. Furan has 2 lone pairs on oxygen. One of those lone pairs is in a p orbital that can be part of your pi cloud, and one of those p orbitals is in the wrong place. It's perpendicular to the other. That's in a hybrid orbital. That cannot be part of your pi cloud. So when we said back here that allylic lone pairs count but only one atom, it's really because, oh, clicky cookie, come on. It's really because that second lone pair cannot be in a place where it's able to share as part of the cloud. One more example. Pyridine has a vinyl lone pair. Vinyl means directly connected to an atom involved in a pi bond. We'll show you that in a moment. But because that lone pair is vinyl, it's in a hybrid orbital. The p orbital is being used already to make a pi bond, so that leaves the lone pair having to be in a hybrid orbital. When it's in the hybrid orbital, it's perpendicular to the p orbitals, cannot be part of the pi cloud. Okay. So, again, I say pyridine has already got a pi bond right there, so that p orbital on nitrogen being used for the pi bond. Pyrrole does not have a pi bond on that nitrogen, so that lone pair is in a p orbital. All right, if we're going to go through here and put little V's and A's, this is pyridine, has a vinyl lone pair. Pyrrole has an allylic lone pair. Imidazole down here, that lone pair is allylic, that lone pair is vinyl. Furan has an allylic, but only one pair counts. Purine, if I'm starting all the way on the left, that's a vinyl, that's a vinyl, that's a vinyl, that's an allylic, that's a vinyl, that's a vinyl. So if we use that designation to go through and count, it means pyridine has 6 pi electrons, just like benzene. It's aromatic. It means pyrrole has 6 pi electrons, just like benzene. It's aromatic. It means imidazole has 6 pi electrons, just like benzene. These guys don't count. These 6 do count. Just like benzene. Imidazole, aromatic. Furan, yep, 6 pi electrons. We're going to get to an example momentarily that doesn't have 6. We don't count it. We don't count it. We don't count it. We do 10 pi electrons. 4n plus 2 equals 10. N equals 2. Purine is aromatic. Pyrimidine, nope. 6 pi electrons. Oh, that's a pi. Yep, it's aromatic, just like benzene. All of your DNA and RNA bases are aromatic. So there are some that are purine bases. You've heard that before, I think, probably. There are some that are pyrimidine bases. These are aromatic. We could go through and put on their lone pairs and figure out what lone pairs count and what lone pairs don't. All the vinyls don't. That means this one don't. So we've got 10 pi electrons, just like purine. It's aromatic. Guanine, you probably need to look at the resonance of that amide bond in order to see why it's aromatic. These electrons count. Those electrons count. Those, and those electrons count. 10 pi electrons, it's aromatic. 2, 4, 6 pi electrons. 2, 4, 6 pi electrons. 2, 4, 6 pi electrons. Yeah. These pyrimidine bases are different to look at and to see as aromatic. I mean, they're not different rules, but it's just students don't always see that immediately. If I drew resonance of the amide over there, you can tell in the middle of this ring now there's a benzene pi, single pi, single pi, single. Yeah. That amide resonance makes all of these aromatic. Being anti-aromatic is useful in medicinal and biochemical things as well. This molecule has 2, 4, 6, 8, 10, 12, 14, 16 pi electrons. 4n plus 2 equals 16. 4n equals 14 over 4, 7 halves. That's not an integer. That's not aromatic. 4n equals 16. 4n equals 4. That is an integer. It's anti-aromatic. That compound that's anti-aromatic is an antipsychotic. This specific compound is an antipsychotic. We've said these molecules need to be flat, but actually because of this central ring causing different interactions, it causes the molecule to be butterfly-shaped. So there's a bend in the middle bond, and this benzene is straight, and that benzene is straight, and they're kind of two wings of a butterfly pointed down. If it weren't that shape, it wouldn't fit the right receptors in our bodies, in people's bodies, to be an antipsychotic. So the shapes of molecules, super important, and if that ring were aromatic, if that molecule were aromatic, it would be totally flat, not fit the right receptor. So it is kind of useful. Okay, more benzene stuff next.